In this video, we're going to solve two problems. The first problem is an MMK system where you have multiple servers, and the second problem is a service design problem where you have two different staff with different service rates and which one should you use. So here we have to calculate the cost of waiting and so on. So let's start with the first one. So this problem is about the fantastic styling salon, and we have three stylists, Jenny Perez, Jill Sloan, and Jerry Tiller. Each stylist is capable of serving 3 customers per hour. So that's your service rate. So mu is going to be 3 customers per hour. Okay. We're not going to use what this type of software is suggesting. It used to come with older versions of the book. I've given you all the tools you need to solve these problems if you go through the lecture and the slides. And I've uploaded an Excel file which I'll show you how to use those tools. So if all customers wait in a common line for the next available stylist, how long would a customer wait in line on average before being served? Okay. And we know lambda because during busy periods 6 customers arrive per hour. So lambda arrival rate is 6 customers per hour. K, the number of servers, is the number of stylists, which is also 3 because we have 3 stylists. Okay. And we have to find WQ, the time spent in the waiting queue for an MM3 system. So this is MM3 system where K is 3. Now, if we go to the slides, we have the formulas for an MMK system given in the slides, and we know that P naught is a bit of an involved calculation, but we can look up P naught in a table, or we can use an Excel file that I've provided to calculate P naught, and then we can calculate the rest of the stuff. We need to get to here WQ, which needs LQ. So we have to find LQ, which needs P naught. So the usual steps in MMK problems are: first you find P naught using the Excel sheet I've provided, then you find LQ, and then you can find all the other stuff that you need to find. Okay. And now we do know this is MMK because we know that we have a system like this where you have multiple stylists, 3 of them, and you have a single common queue. So people queue up, and whichever stylist is free, they go to that stylist. If we had this setup, we'd analyze it differently as multiple MM1 systems, which we'll do in this problem later on. But right now we have one shared queue, which means it's an MMK system, and this was explained in the lecture video. Difference between MMK and multiple MM1 systems. So first order of business is to find P naught, which depends on lambda, mu, and K, and we know these values. Okay, so we have to find WQ, and for that the first step is to find P naught. Now to find P naught, we can go to this Excel sheet that is given to you, provided to you, and you can put in your parameters, and it calls a compute P0 function that I coded in Visual Basic, which is built into Excel, that computes P0 for you. So we know that our lambda is 6, our mu is 3. It'll give you an error because right now you don't have enough capacity to handle 6 customers because K is 2, but we have K is 3, so we set K to 3. And with 6 arrival rate, 3 service rate, and 3 servers, we get P naught to be 0.1111. Okay, so we can go here and put P naught is 0.11111. Okay. Next we have to find LQ, because if you go to our slides, if we find LQ, then we can solve for WQ, because WQ depends on LQ. So LQ is a little bit of a complex calculation, so I'm going to do it in 2 parts. I'm going to calculate this top term and call it part 1. Then I'm going to calculate the bottom term, call it part 2. Then I'll divide the 2 and multiply it by P naught, which I already have. So for LQ, I'm going to do, part 1, and then part 2, and then the final LQ value or calculation. Okay, so part 1, I can see from this formula is lambda over mu. Okay, and then you raise to power K, multiplied by lambda, multiplied by mu. So I take lambda, I divide by mu, and I raise it to the power K, and then I'm going to put all of this in bracket, so I make sure that the raised to power happens before multiplying by lambda, and then I multiply it by mu. So I put in this exact formula. Now for part 2, I have to first take a factorial of k minus 1. So I do fact k minus 1. Then I multiply by, now when you take the factorial, you have taken care of the exclamation mark. That just means factorial of the number here, k minus 1 factorial. Then just have this bracket which is squared to the left. So I have something in bracket which is going to be squared. So in brackets I have k times mu minus lambda, and then I have to square that. And so then my final calculation is going to be the part 1 divided by the part 2, and after the division is done, multiplied by p naught, and my LQ is 0.888. Now once you have that, you can find WQ is LQ over lambda. So WQ is going to be LQ divided by lambda, and this is going to be hours. So this is WQ in hours. Now we need WQ in minutes. Now why did we calculate WQ in hours? Because all the numbers were given to us in hours, but we can always convert this into minutes by multiplying it by 60, because there's 60 minutes in the hour, and this is in minutes to 2 decimal places. That'll be 8.89 minutes. Okay. Next part, suppose that customers want to be served by specific stylists. So 1/3 want Perez, 1/3 want Sloan, 1/3 want Teller. So now we are moving from this picture, which was MMK, to now this picture where we have 3 stylists. Instead of 5, we have 3, and each one have their own queue. So people who want Perez will queue up for Perez. People who want, Tiller, queue up for Tiller, so on. So we have 3 queues, 3 stylists. We have 3 MM1 systems. Okay. So let's go back to the problem. So now we're going to do 3 MM1 systems. That's always an alternative, and this was an MMK system. So instead of MMK, we go to, which is k equals 3 instead of MM3. We now go to the alternative, which is 3 MM1 systems. Okay. The average waiting time is this. So now for this one, lambda arrivals are still the same, customers per hour. Oh no, actually the arrivals are going to be different, because 6 customers arrive for all 3 stylists, but how many customers go to 1 stylist? That's going to be 2, because 1/3 times the old lambda will be the new lambda. So lambda for each individual stylist is going to be lambda per stylist. Is going to be 1/3 times the old lambda, which is going to be 2 customers per hour. Mu is going to stay the same, because each stylist is working at the same rate, 3 customers per hour. There's no k, it's just 1. It's the MM1 system. And so we have to go to the slides for the MM1 system formulas, which are right here. And we find WQ, which depends on LQ. LQ is right here, lambda squared over mu times mu minus lambda. And so first we will find LQ and then WQ. So for LQ, we're going to first square this new lambda, and then we're going to divide by mu multiplied by mu minus lambda. Okay, and so we get 1.33, and then WQ is simply LQ over lambda. That's going to be LQ divided by this new lambda, and that's 0.66 hours. Okay, now the question wants us to put in minutes, so again we'll do this times 60 to get minutes, and the waiting time is 40 minutes. So notice, by going from an MM3 system to 3 MM1 systems, we have increased the waiting time so much. From less than 10 minutes, about 9 minutes, we're going up to 40 minutes. Huge. We're very worse off. So that is why, as explained in the lecture, this MMK system with the same number of servers is a much better in terms of reducing waiting time than multiple MM1 systems. Okay. And we talked about in the lecture why sometimes we still go with this one, why some companies go with this one over this one, but this one is superior. Okay. Okay, so part C. If customers wait in a common line for the next available stylist, how long would a customer wait in line? before being served. So we just did that here. I'm just wondering, how is that part different? Part C. Oh, okay. So we have this new information during less busy times of the day. So you have to evaluate this situation now. We have this new information. During less busy periods of the day, 4 customers arrive on average. So this was the busy period calculation. We're going to go down. We're going to down and do less busy times. And now lambda is 4 customers per hour. Okay, because we're not as busy to get 6. And now we only have 2 stylists. So we have an MM2 system. So mu is still 3 customers per hour. K is 2. So your MM2 system. And what is WQ? Okay. Okay. So the easiest thing is we could redo the whole calculation here, but we did this huge calculation here. The easiest thing is just to change the K to 2 and the lambda to 4 and get the new P naught. And so if we go here and we change the arrival rate to 4, okay, and we have 2 servers and mu is 3, the P naught becomes 0.2. So P naught becomes 0.2. This becomes 4 and this becomes 2, and all of these formulas automatically update to give us the WQ for part C. Okay, so this is for part C now. So we just get 16 minutes. We need to round it to 2 decimal places. Let's make sure there are no hidden decimals. There are none. So we should have 16 minutes. Well done. Okay. So now, suppose we're still in this situation. So this is going to apply to all the parts below it until we get any new instructions. So we're still 4 customers arriving, 2 staff, Perez and Salon. Now let's say that it's not equal split. 60% want Perez and 40% want Sloan. So we are going to go into the situation with 2 MM1 lines. Okay, so we're going to go to this situation where Perez has his own line, Salon has their own line, Perez has their own line, and the lines are not the same. 60% customers go to one line, 40% go to the other line. For Perez, 60% want Perez. So we are going to do this MM1 system. Okay, so we're not using that. We're going to do this MM1 system, and let's do it for Perez first. So for Perez, the lambda is going to be 60% of the overall lambda coming to the shop. So it's going to be 0.6 times. How many customers are coming? 4. So 4 are coming. So 2.4 customers are arriving for Perez. Okay, and Perez's service rate is obviously 3 customers per hour, same as last time. And so how long do you wait for Perez? You wait 80 minutes. Okay, now for Sloan, 40% customers want Sloan. So 0.4 times 4, or 1.6 customers want Sloan. Service rate is 3 customers per hour. They wait 22.86, 2 decimal places. So 22.86. Okay, so the waiting times are different for the 2 stylists because different numbers of customers want them. What is the overall waiting time? So if for Perez, people wait 80 minutes. For Sloan, people wait 22, this amount of minutes. Then what is the overall waiting time? Okay, overall waiting time. Well, we know 60% or 0.6 proportion want that, 40% want that. So the overall will be a weighted average, 0.6 times 80 minutes plus 0.4 times, 22.86. That'll be 57.143 or 57.14. Okay, and that is the kind of weighted average waiting time for that. So we did an MMK calculation, then we went to 3 MM1 systems, then we went to an MM2 system, and we went to 2 MM1 systems with different arrival rates because some more people wanted Perez than Sloan. So we did various configurations of this Salon to see how the waiting time is affected on how, depending on customers, whether they're okay with a common line or they want separate lines and so forth. Okay, let's go to this problem here. And this problem is interesting as well. So we are a supervisor at Precision Machine Shop. Okay, Okay, so precision machine shop. We want to determine the staffing policy that minimizes total operating costs. Average arrival rate at the tool crib, where tools are stored, is 5 per hour. So lambda is 5 machinists per hour. Okay, each machinist pay is $5 per hour. The supervisor can staff the crib either with a junior attendant who's paid 11 per hour and can process 12 arrivals per hour, or with a senior attendant who's paid $18 per hour and can process 16 arrivals per hour. Which attendant should be selected? Now, we are going to have a cost of waiting because these machinists are being paid, okay? And so they are going to end up waiting. And that is a cost. And that waiting cost is going to differ between the two. Actually, even the service time is going to vary because one attendant is slower, one other one is faster. Okay. And then we also have the cost of the server, which is whether we go for $11 per hour person or $18 per hour person. Now you might say this problem has a very low salary for the machinist, it's only $5. The question generates numbers kind of randomly, and so in this iteration it's showing you a very low salary, although you would expect the machinist salary to be much higher generally, right? So we did a problem like this in the lecture examples where we had to find the cost of trucks waiting, right? And we remember that our waiting cost is whatever it costs to keep that employees or equipment waiting times the number of people in the system L. So we're going to do the same thing. We're going to multiply the machinist salary, dollars, whatever their wage rate is, by L, the number of machinists in the system, because they're not doing their machining job, they're waiting to get the keys or getting the tools, right? And then we can add the cost of the service, okay? So we have two scenarios. So we have scenario 1 and then scenario 2. In scenario 1, we have mu. Okay, mu is different for both. So if we pick a junior attendant, we can process 12. So mu is 12. And so this is the junior attendant. Okay, and this is the senior attendant. Okay, and if we pick the senior attendant, mu is going to be 16. Okay, and then the salary of each attendant is different. So what is the L when mu is this, and what is the L when mu is this? Lambda is this. So we go to MM1 systems because there's only one server, right? Either a junior or senior. We don't have both servers, and so we need L, and L is LQ plus lambda over mu, and this is LQ. So we find LQ, and we find L. Okay, and then we can find the waiting cost. So we need LQ and L. After that, L. Okay, so for LQ we take lambda squared. I'm going to put it in brackets to make sure the squaring happens before I divide it by. Oops, this is the right formula. LQ. I was on the wrong slide. This is MM1 example. So it's lambda squared over mu times mu minus lambda. Okay, so divided by mu, which is right here, times mu minus lambda. Okay, and I'm gonna put dollar signs around the lambda because if I copy the formula, I don't want the blue cell to move. The blue cell should remain locked. Okay, and that is going to be my LQ. I forgot to close one of the brackets, and I can just drag it here and get the LQ for the senior attendant as well. Okay, now L is just going to be lambda over mu added to L of Q. So we take L of Q plus we take lambda, and again I'm going to put the dollar signs, press the wrong key here, okay, and divided by mu, okay, LQ lambda over mu, and then I can just move it here, and that's again same lambda, so LQ plus lambda over mu. So LQ this, and then lambda over mu. Perfect. So that's our L. And so then our waiting cost is simply the salary of the machinist, which is salary of machinist, which that's $5 per hour. And so at any given time we have this many in the system in any given. So we do L, this is the number of machinists waiting, multiplied by their salary, and this will be waiting cost in dollars per hour. So each hour the system operates, we are spending $3.57 dollars because the machinists are stuck getting their tools and they're not able to work. Okay, so we take the opportunity cost of doing this, which is we're not using the machinists to do what they need to do, and we are instead making them wait for the tools and so forth. Okay, so again we put dollar signs here, then I can just drag it here, and in the other system this cost is lower. Now we also have the cost of the system, the serving system in dollars per hour, and that is simply the salary of the junior attendant and the senior attendant. Junior attendant, the salary is $11 per hour, and the senior attendant, the salary is $18 per hour. Okay, so the total cost will be waiting cost plus the cost to provide the service. And if we go for the other one, it's going to be this. Okay, so in this case it costs a lot less to go for the junior attendant because the waiting increase is not that much. The waiting cost increase a little bit, whereas we save a whole lot of money with the junior attendant. Now in real life, you are not just paying for the machinist salary, you're not just paying the machinist to be idle standing in line, you're also losing some revenue because machinists are not able to produce the product. So usually the waiting cost will be higher than what we have estimated here, but this is to keep the example a little bit tractable and simple. So we're only given their salary, so we have only this waiting cost. If you are also given, okay, they produce products worth this much per hour, then you would add, and if they're waiting, they're not doing that production, then you would add that cost of lost production per hour to the salary and then multiply by L to get the waiting cost. Okay, so we are going to use the junior attendant, total cost of $14.57 dollars, okay, which is right here. So that's how we can decide between which server. This analysis can be used very well. You decide if it is a more expensive machine which works faster, it's going to shorten your queue. So what is the benefit of that? You pay more to get the machine, but does the waiting cost reduce enough, and so forth. So you can do this sort of analysis called service system design or service system design to figure out what's the ideal optimal decision for you.